talk as part of the theory seminar series. We are glad to have Sahil Singla with us today. We'll be talking about robust secretary algorithms for packing integer programs. So brief bio about the speaker. Sahil Singla is currently an assistant professor in the School of Computer Science at Georgia Tech. Earlier, he was a postdoc jointly between Princeton and the Institute for Advanced Study. He received his PhD from CMU. His current research focuses on algorithms and uncertainty, and the goal being in this scenario to design optimal algorithms for uncertain inputs. With this, I hand it.
Yeah, thank you. Thank you so much for the invitation. Yeah.
All right.
Good. So yeah, today I'll be talking about some robust secretary algorithms. And yeah, feel free to interrupt me anytime with questions. I want it to be interactive. Unfortunately, I don't think I can see your faces right now, like I'm on my iPad. And but yeah, so just interrupt me. I don't think I'll be able to monitor chat. Good. So I'll be speaking on this robust secretary algorithms. The talk will be primarily based on two works. First of them is from SODA earlier this year. This was joined with Marco Molinaro, CJ Argue, and Anupam Gupta. And the other work is from a couple of years old with Anupam Domagoi and Goran Sujic. So the talk will be primarily based on these works, but I'll talk about some other works here and there as well. And yeah, as I was saying, like feel free to interrupt me any moment. Good. So at a high level, what's the pitch in some sense? Where should you view this work? So we've been doing a lot of algorithm design, and traditionally algorithm design can be broadly classified into like one of these two categories. On one side, we have the worst case algorithm design, where you get the worst case input, and you want to get a guarantee on the performance of your algorithm, even for any kind of input. For instance, in undergraduate algorithms, we often talk about running times for the worst case inputs. Another kind of extreme is under some kind of a stochastic or an average case analysis, whereby you assume maybe your input is coming from some distribution, maybe known, unknown distribution. You want to design an algorithm which on average in expectation has a good performance. There could be some inputs where it doesn't do much, it doesn't do well, but on average it should be fine. And I mean, both of these have some benefits and pros and cons. Like for instance, the worst case algorithm design is very robust. It gives you worst case guarantees. But often for many problems, maybe online streaming, even worst case algorithm design, what you cannot show is that, that you cannot get very good performance guarantees. It's easy to prove that maybe you cannot do much for these worst case problems. On the other extreme, for these stochastic problems, you can often get strong results just because you have more assumptions, so you can actually obtain much better guarantees. However, these algorithms are often too stylized to the underlying assumptions. So whatever is the underlying distribution. So the natural question that we want to ask is that, okay, what happens if you have an input which is maybe coming from well-behaved, which is coming from some underlying distribution and so on, but what if there is some noise to it? Or like, what if there's some small adversary playing some role? Like, because naively, as soon as you change the assumptions on your input, all bets are off. Like in this stochastic design, you basically only have guarantees for this particular distribution input, but what happens if we have something in between? So the question we want to ask is, can we handle, for instance, noise in this stochastic models? I mean, at a high level, the way I view it is basically you want to design some kind of robust algorithms. So these are algorithms which are robust to noise, outliers, whatever you want to call them, some small adversarial behavior. And today's talk will primarily focus on the stochastic problem of the secretary instance. I'll explain the problem on the next slide. So in the context of this secretary problem, we'll see, okay, what can you show under fully stochastic assumptions, under fully worst case, and how to interpolate between the two. And briefly, I'll mention about some other problems as well, like the profit problem, but the talk will primarily just focus on the secretary problem. Good. So again, yeah, feel free to interrupt. So what's the high level, the secretary problem? Many of you have probably heard it. So the way I want to view it in this talk is in a continuous time kind of a regime, whereby your time horizon is from t equals 0 to t equals 1. You're going to get n inputs, n numbers values, like say non-negative reals. These numbers are unknown to you. So a bit more formally, these n numbers are chosen by an adversary up front. So these are v1 to vn. However, the sequence in which they arrive, that's not under the control of an adversary. So each of them chooses each of these numbers, it chooses a uniformly random time between 0 and 1 in which it arrives. And so basically imagine like your timing is increasing from 0 to 1. As soon as the time of an element comes, it just shows up. It tells you its value. When you get to see the value of the element, you have to immediately decide, are you taking it or not? You can only take in total one element. So that's the setting. And your goal is to maximize the expected value that you're getting. So this is the problem. So to give you like a small instance, maybe at some point you get to see some value V1. Now, the thing is like you have no idea how large is V1 compared to the other numbers from V1 to Vn. So maybe you decide not to take it. Maybe you get to see a V2, which is a larger value. So y-axis here represents the number, like the scale of the number. V3 comes and then V4 comes. So I mean, at some point you maybe decide like maybe you stopped at V2, so you get a value of V2, but ideally you should have taken V3 in this case. A remark like, so many of you might have heard of the secretary problem just in the random order instead of like choosing uniformly independent times. I mean, both the models are kind of the same, but I'll view it in this time version because it simplifies some of the things which I'll be talking about today. Okay. And so this is the classical secretary problem, and it has applications in many, many settings, online algorithms in particular, because you have these inputs arriving. It also has a lot of applications in algorithmic game theory. For instance, you want to sell an item, you want to maximize the amount of money you're making out of it, and so on. So I won't be talking much about the application, but this is a very standard problem, like more than 50 years old, the secretary problem. And so what? Yeah.
So you're indexing in the order of the choice of the TE, or that's just this picture here?
Yeah, so I'm mostly going to index them in the sequence in which they arrive. So not exactly in the time. Yeah.
Okay.
Good. Yeah, and there's a simple constant approximation algorithm for this problem, which is known as the Dinkin's algorithm. So what this algorithm is, just ignore all the elements that arrive before t equals half. And otherwise, in the second half, basically, you select the first element, which is larger than all the previous ones. So if, for instance, like none of the elements is larger than all the previous ones, then you don't select anything. But if any of them shows up to be larger than the entire prefix, then you select it. And there's a very simple argument why this algorithm works, because basically the probability that you'll select the largest element is at least the probability that the largest element, its arrival time, so I'm calling it T max, that arrives in the second half, so it's greater than a half. And the probability that the second max, its arrival time is less than half is also a half. So if both these events happen simultaneously, then you're guaranteed to select the largest element. So there could be other settings as well where you might be getting the largest element, but this already shows you that you can get the maximum element with at least a constant probability. So the expected value of your algorithm is already like at least a factor, quarter, like times the max. And I mean, you can do better analysis. In fact, what's known as for this problem, you can even get like the tight ratio between the expected value of your algorithm to the Vmax to the largest element. You can improve it to 1/e, which is roughly 37%. But in this talk, I won't worry too much about constant factors. So any constant factor, I'll be like very careless about losing them. So, but yeah, so this is the classical setting. This is in the fully stochastic model, where in the fully stochastic model, I mean, each of these elements that each of these numbers values that they are arriving, they're choosing their arrival times uniformly, independently. So
Sahil, one question. So to get 1/e in Dinkin's framework, what do? You choose t to be some other value, or you're okay?
Yeah, so just choose t to be instead of half, choose t to be 1/e, which is like slightly to the left, like 0.37. Yeah.
Okay, same like a random order setting. Also, there you discuss the first 1/e fraction.
Yeah. Okay. Yeah, so it's basically the same thing. In fact, the proof only simplifies here if you look at this continuous time view.
One question. So isn't the second probability, shouldn't that be a conditional one?
So this is the good thing about this. Like I'm thinking of each element arriving uniformly, choosing its own arrival time. So even if I condition on the max one arriving in the second half, the second element is independent because everybody is choosing their arrival time independently. So these are like, for instance, this is an example, an inequality which is kind of obvious when all elements are behaving fully independently. Whereas if you're working in the random order model, then you have to talk about this conditional probability because like then the threshold you set to is to be roughly like n/2 elements. Now remember, like the number of elements that arrive in the first half is not necessarily exactly n/2. It's in expectation n/2, but I mean it will have some distribution around that. So these are some of the inequalities, for instance, which kind of get simplified if you think of the continuous time view. But yeah, the proofs also work.
But if we use 1/e instead of 1/2, we will get this 1/e fraction, right?
No, I think you will still get 1 over E. But yeah, it's a minor thing. As I'm saying, like in this talk, we want to worry about constants. Yeah. Okay, good. So let's
also,
continue.
like the advantage of this continuous sort of view is that you don't have to know n exactly upfront.
That's exactly, could be again one of the assumptions. Some other benefits are also like it simplifies things because different elements are behaving fully independently, as I was mentioning. Otherwise, if you condition on some element arriving at some position, that kind of changes the conditional probability of other elements.
Correct.
So such things kind of simplify. Good. Okay, so this is the stochastic view. And you might naturally ask, okay, why do I have to make this stochastic assumption? What happens if these numbers were arriving fully adversarially or the worst case arrival? So why not consider the worst case model? And here's a very kind of more like a mathematical kind of an answer that is, in some sense, you cannot hope to do much for the problem if they arrive in a worst case. And the rough underlying intuition is because you don't know the scale of the problem. You don't know whether you're fighting for pennies or you are fighting for billions of dollars. So an instance is the following. So this, remember, this is again, the numbers are chosen by an adversary, and now even the arrival times are chosen by an adversary. So what could happen is you're getting these numbers which are increasing very fast. Maybe the first number is like, say, $1. The second number is $1 billion. The third one is a billion square, billion cube, and so on. So each successive number is insanely larger than all the previous ones. Or at some point, after some I star, like which you don't know, all the successive numbers will be just zeros. Now, basically, in such kind of an input, you have no idea how large the numbers, like how large is the max, and there's not much you can do. I mean, you can prove using simple minimax or something. That the best you can do is roughly like a 1 over n. You can select one of these n numbers uniformly at random, and so in expectation, you get roughly an n approximation. And I'm thinking of n to be pretty large, so much larger than any of these constraints. So yeah, so in some sense, like the answer that I have is that why am I assuming this like stochastic arrival or random order model is kind of like because it's mathematically necessary. And then I can also try to justify that there could be many applications which are more well-behaved, the input is more well-behaved, so this assumption makes sense. Maybe there's no adversary acting against you, and like you expect things to arrive maybe at uniformly random times and so on. So yeah, that could be another justification, but in some sense, like the reasons are of the form, like it is mathematically necessary because in the worst case model, you cannot really do anything besides this trivial n approximation. Good. And yeah, but still, like, so this model of secretary model, like this, or like the uniform arrival time, stochastic arrival time, that has been greatly studied. It has been very, very successful for many, many online problems, primarily because these are problems where in the worst case model, you cannot hope to do much. Like already, for instance, for selecting a single element, the best I can do is just n approximation. And the problems become only harder if I want to select like multiple elements, if I put a packing constraint, like if I want to solve an LP, if I want to solve like matchings. And like, so the more I talk about any of these other problems, they are even further hopeless in the worst case model. But in the secretary or like this random order arrival or this uniform arrival time model, you can actually do much better guarantees, perform much better guarantees. And in this talk, I'll be talking more about this packing linear integer programs as well later in the talk. Good. So this is the worst case model and the stochastic model. So now what do we know about the two extremes here, for particularly the secretary problem? On the left-hand side, we have this random arrival or the uniform 0-1 arrival order. On the right-hand side, we have the worst case arrival order. In one case, you can get 1 over E. In one case, you can get a 1 over N. The question is, okay, what can we do if you have some kind of a mixed arrival? So maybe your input is kind of well behaved. It has like most of the elements are arriving uniformly at random. Okay. But what if a few of those elements are adversarial, or maybe you have no idea about them? They're not coming from some underlying distribution. They may be chosen by an adversary. Like naively, is there anything we can do, or like all bets are off? Is it already like totally hopeless? So that's the main question we want to study. Okay, and what we'll see soon is that, okay, simple algorithms like the Dinkins algorithm no longer work, even if you have like, say, a single adversarial arrival. So you need to do something more. Existing algorithms, they are not robust. So I'm trying to say that it's robust. So I'm thinking of more like my input is stochastic. At least the good part of the input is stochastic, but there are some adversarial inputs, and I want to be robust against them. Okay, so any questions? Good. So if not, like, yeah.
So when you say underlying distribution, it's the distribution for the time arrivals. The values are always adversarial, right? In all the models.
Yes. Yeah, good question. Yeah. Okay, so let me now introduce this Byzantine Secretary model that we introduced in the ITCS 20 paper, the 2 years old paper. So the name was inspired from the Byzantine generals problem, distributed computing, many of you might have heard, where basically you want to talk about a setting where you have some well-behaved agents, but there are some adversarial agents as well. So what is this Byzantine model? So as I was saying, I want to study mixed arrivals, and I want to think of two kinds of elements. So red and green elements. And as the colors might signify, so red are kind of the rogue or the bad or the adversarial elements, whereas the green are the well-behaved elements. So green are the elements which still arrive uniformly at random, like IID, their times are uniformly in 0 to 1, whereas red elements are placed adversarially. So more formally, like you have these n numbers, where n is equal to the sum of the cardinalities of both the red and the green elements. Total number of elements is still n. All of these numbers are chosen by an adversary, including the green elements. As the question was raised, everything, the numbers are still fully adversarially. Then the red elements are placed by an adversary. Their arrival times are also chosen by an adversary. So you have no control on the arrival times of these red elements. These red are the bad elements, the adversarial elements. The green elements then choose their arrival times uniformly from 0 to 1. So remember also, like, the sequence is kind of also important. Like, we are first placing the red elements and then the green elements. So the red elements are maybe not adaptive to where the green elements land up. One could consider those models, but like I think this one is more natural, where you imagine that the red elements first choose their arrival times and then the green elements uniformly arrive. And again, the model is the same. Now you have a continuous time, so time gradually increases from 0 to 1. Whenever you reach an element's time, its value is revealed. You have to immediately decide, are you accepting it or not, and you want to maximize the expected value. Okay, and of course, just to highlight this, that when you see a value of a number, you don't know whether it's a green or a red element, whether it's a stochastic or a red element. Because if that was the case, I mean, somehow the problem becomes much simpler. Because I mean, you just kind of are back to like two separate instances. So yeah, the question is, in this mixed arrival, when you don't get to see the values, the type of the element, how do you go about designing good guarantees?
So Sahil, like just
Yeah.
Dinkin's algorithm will fail, right? At time 0, I can give you the maximum. And
perfect. Yeah, exactly. So that was my next bullet point.
Okay.
Like, yeah. So Dinkin's algorithm is not at all robust in this setting, because even a single large adversarial element. So the adversary could present you one large element, which is larger than even the largest green element in the beginning, right in the beginning. So if you set a threshold of that element, you'll basically end up not selecting anything. So you've already, like, this shows that like only a very little corruption can already fully destroy the guarantees of your classical secretary algorithm. So we want to design some algorithms which are robust. Okay, and
Sahil,
you might go ahead.
Yeah, so when you say all n values are adversarial, what do you mean by that? Because
so
only
these
the green
numbers
one.
we want to n, these numbers are chosen adversarial. Like maybe one element is like $1,000, the other one is $1 million, and so on. So these numbers are chosen adversarially, but their arrival times, the red elements, their arrival times are also adversarial, but for the green elements, their arrival times are uniform. Like in the classical secretary problem also, like all these n numbers are still adversarial. You don't make assumptions on them.
And the adversary knows our algorithm, like that.
Sorry?
Okay. Adversary knows our algorithm, right?
Yeah, the adversary knows our algorithm.
Exactly.
One question. So the adversary is allowed to, like, he knows which values become red and which ones become green, right?
Yeah, because in some sense, the adversary is choosing what these red numbers are, where they land, and so on. Yeah. So the adversary does know. So the only thing that the adversary does not know is the arrival times of the green elements. So it's oblivious to the arrival times of the green elements, but it knows the values of the green elements and so on. Okay.
Yeah, one question.
Yeah.
So, like earlier with just the green items, it is sort of equivalent to having all permutations. Like if I want to look at the permutation world, what sort of permutations are ruled out because of this?
Oh, you mean like, I guess, what's the difference between the two models in the arrival times 0 to 1 and yeah, so that's a great question.
With the red elements, I guess with the green elements, they would be sort of equivalent, right?
Exactly. So that's a great question. So honestly, I don't know. So many of the results that we were showing, we could kind of show them in both the models, but the proofs and many of the things were getting much more ugly. And morally, both the models to me are kind of equivalent. So honestly, I haven't tried to figure out whether every result can be extended. but many of them were kind of extending to both the models. But yeah, but you're correct. I don't know of an equivalence between the two models. So there are some things. So as we'll see like later on as well, like, I mean, for instance, I want to say, like I want to divide my partition my time into some time horizons. Like say I want to put this threshold of half time. Now these things become very different in the two models. Because if you are putting n/2 as your cutoff versus putting a time horizon of half, there's a difference between the two models. In n/2, it could be like, for instance, if there were like n/2 red elements, maybe all of them were n/2, they arrive in the first half. Whereas if I'm putting a time window of half, then in some sense, all the red elements could still arrive, but the green elements still, each of them has half a chance of arriving in the first half. So there are, yeah, I mean, that's a very valid question that, yeah, the two models, to some extent, they are similar, but there are, I mean, differences between them.
You see, thanks. Sir.
Also, you might want
any
to
restrictions.
Sorry, can you repeat? Yeah.
Sorry, go ahead.
Arun. Okay, so I was asking that. Yeah, deadlock. You can go ahead. Yeah.
I'll ask quickly. Is there a restriction on ratio of red to green element?
No, we are not making any assumption at all. I mean, for some of your applications, you might want to think of red being like much smaller, like say 5% elements, but our results will be independent. So it could be like the number of red elements could be 99%. So it could even be that there's only like 1% green elements, or like maybe just 1 or 2 green elements and everything else is.
And the algorithm knows this, does not know this, like the split. How many of them are red? Like a priori.
Yes, so we will not assume that. Yeah, so we don't know the split.
Okay.
So for some of these problems, I might assume that I know n, but yeah, even that, yeah, I'll get to that in a bit. Yeah.
So here the adversary you need to be like put more restriction, because one is ordering, that is already you are showing that it is not robust, but also the values. If adversary always chooses red elements to be very high compared to green elements, then basically green elements are not adding any value. It's basically red elements which are
yeah, exactly. So you're basically, yeah, that's a great point, and this is exactly my next slide. So the question you're kind of asking indirectly is that what's even the right benchmark? Like what should I be competing against? Can I hope to get the largest element overall, or like what can I hope to get? And this is what the question is, like, okay, what should be the benchmark? Earlier, like in the world of fully stochastic, I wanted to always get the max value. Like what is the max value? Like, can I show something? So one option would be overall max, which is the max of all the green as well as the red elements. But that's easy, as you were pointing out, that yeah, you cannot actually do much because all the green elements could be just 0. And then you're just back down to red elements. And for fully adversarial arrival, the best you can do is like order n, where n is say the number of red elements. But I'm imagining like the number of red elements to be omega n, so you cannot really do much. So you have like many, many large elements. So overall max is totally not at all achievable. Next natural thing would be, okay, can I achieve the max green? Like at least can I get the max of the stochastic elements? And unfortunately, the answer is actually you still cannot do much. So it turns out even if you want to compete against the max green, the best you can do is still roughly like the number of red elements, that competitive. So like order n competitive. And the arguments are of the proof. I mean, it's not super important that you follow it, but like it goes as follows. Like again, you have maybe say a single green element, which is large, and you have an increasing sequence of reds. Now, somehow, if you see, yeah, just seeing if I can have a pointer. Okay, I'm not sure if you can see my cursor, but yeah, you have an increasing sequence of these.
We can see the pointer.
Okay, you can see the pointer. Good. So yeah, you have this increasing sequence of elements, and like so, the first element comes, then say like $1 billion square and so on, or like some sequence. Now, when this third element comes, it's again super large as compared to all the previous ones, but you've no idea to determine whether this is a red element or a green element. Like in some sense, you cannot differentiate between the two. So each time step, you still have to kind of make a random decision whether you want to stop or continue. And you can formalize this again using your minimax and argue that you cannot really hope to do much. Okay, so even the largest green is not achievable, which is kind of like a bit unfortunate. And so the question becomes, okay, what can I hope? Like, so, I mean, it's already showing like this Byzantine model, this adversarial arrivals, they do create a lot of complications because the largest green
but
no longer. Yeah.
if we have like say, green and red almost similar in number, then this problem should not happen. I mean, I guess this is fixed.
Remember, like the numbers don't really matter because, like, suppose even if I have too many greens, but all the other greens have value 0. So in some sense, the problem is just about a single green. So they don't really contribute much. It's not about their cardinality because remember, the
I mean, in that case, this green will come. I mean, this high value green in expectation will come near half or something.
Yeah, but that's again like but yeah, it's a uniform arrival order. So yeah, you cannot really.
Okay.
On average, I agree it will come around half, but yeah, you cannot really say much. Yeah.
So it's the scale of the red items that is the issue here, right? We don't know the scale of these items.
Yes.
Red items.
Red, green, yeah, in some sense, exactly. Yeah. So the scale of the problem. Yeah. Good. So the question is, okay, so we kind of need to make further assumption or need to like further relax the benchmark. So here are two things that two models that I'll talk about, two assumptions or two models, and either of them will work for us. I mean, it won't matter which one. So one assumption that we'll assume, like which one could assume, is that imagine you have some very rough approximation of the largest green. So I don't know what the max green is, like I don't know what the value is, but let me assume that I have a poly n approximation to it. So I'm not assuming like a very good small approximation, I'm just assuming a poly n. So n is large, so you have at least you have some idea, maybe you're fighting for pennies or you're fighting for billions. So it's a very rough approximation. So that's one kind of an assumption you could make.
What is the n here? Poly n, what is the n?
N is the total number of reds and greens.
Okay.
The total number of elements, yeah. Okay, so one assumption could be of this form that, yeah, you have a good approximation on the max green, like the largest one. Again, it's not an approximation on the max red, because max red you cannot really do much, but max green. Another assumption, is that you change your benchmark to be not the largest green, but make it the second largest green. So remember, you have all these red elements, you have all these green elements. Green are all the stochastic elements, like the ones which are in a uniformly at random. So change your benchmark to, rather than being the max, make it the second largest. In some sense, like the way you could think of it is like somehow in this robust model, you cannot hope to get the largest. But as soon as you start competing against the second largest, then actually you can hope prove guarantees. And again, I'm not saying that you have to make both the assumptions. Either of these assumptions will suffice for our results. And I mean, yeah, depending on your application or something like it, one of them might make more sense. And at some level, like the reason I have these assumptions suffice is because they're giving me some rough approximation on the scale of the problem. Like the first assumption is immediately giving me a poly n approximation on the scale. The second assumption also is indirectly what I'll do is because I'm willing to sacrifice the largest green element, I can use that to determine some kind of the scale of the problem, again, up to some poly n factors. So basically assumption B kind of reduces down to assumption A. Yeah, so that's like, but either of the assumptions will kind of suffice. And so the question is, okay, what can we prove under these model? So first of all, for the single item value maximization, the problem that I've been talking about, what we can show is you can get the Logstar N approximation. So by Logstar here, I mean the iterated logarithm. So it's not exactly a constant, but kind of close enough. So in the first paper, the ITCS one, we had, this is from ITCS 2020. It's written, yeah, there's a typo, but yeah. So we showed a Logstar N squared, but yeah, we can improve it like the square as well. We shaved off. So this is the single item value maximization, which I'll be talking about in the talk. The other result is more about packing linear or packing integer programs. So roughly the model here is, I mean, I'll introduce the model more formally later on, but you want to solve a packing LP. So you want to maximize summation VIXI subject to AX less than equal to B. And these are all like non-negative packing constraints and so on. And imagine like your variables are arriving one by one. So maybe the first event alive, X1 arrives, maybe it tells you about V1. You have to immediately decide, are you taking that variable or not? So I'll define it more formally, but under this model, again, this is again something that has been greatly studied, this such kind of problem in the fully secretary model, like under no adversarial rivals. So, but what we are able to show is kind of get comparable results, even in this robust model, in this Byzantine model. So what the exact guarantees are, we get some constant approximations, assuming your budget is slightly large. So you have to make such an assumption even in the fully stochastic model, because somehow you need to be careful that, okay, one bad decision won't really destroy your algorithm entirely. Yeah. So these are the two results I'll be talking about today. And towards the end, I'll also mention a few other results. Any quick questions about what the results are, or otherwise I can go into the technical part.
First one holds under either of the
Assumptions, yes.
Okay.
Yeah, both of them actually.
So do the assumption B implies assumption
A? So I guess it kind of does for our applications. I'm not sure, like for these secretary kind of assumptions models, we are able to show. I mean, I'll soon mention how it kind of does, but I'm not sure if there's like a black box kind of a reduction from B to A. But yeah.
Yeah, thanks.
So if the green points are actually drawn from a reasonable distribution, you do have assumption B by itself, like some sort of order statistic.
Yes, I mean, yeah, so exactly. So yeah, that could be, I mean, yeah, if you can argue like if your input somehow like the largest green and the second largest green, they are comparable in values, then anyways, yeah, it doesn't, that assumption holds. Good. Okay, so as I was saying, the outline for the talk is I mentioned this model of secretary problem, Byzantine secretary. I'll first talk about the single item setting. I won't prove the Logstar N, I'll prove the Logstar N squared. I'll give the idea for this. And then the next part of the talk will be more about these packing linear or integer programs. So I won't, I mean, okay, so for these problems, it doesn't matter whether you're talking about packing linear or integer programs, because you can always do randomized rounding. Under the large budget assumption, basically rounding kind of comes for free. So you can call it packing linear program, packing integer program, it doesn't matter. So yeah, you get a constant approximation, and finally I'll conclude. Okay, so I'll be careful about the time. So at a high level, what's the approach? So this is now I want to talk about the single item problem. So you want to just select the single item problem, which I've been focusing on right from the beginning. Okay, and again, the issue is somehow you want to get an estimate of the scale of the problem. So let's first see like how does the scale, by scale I mean like this, but I was assuming like assumption one, which was the Poly-N approximation or something. So why does any such assumption help? And the reason is the following. So here's the claim, or like a simple observation. So suppose somebody tells me that the optimal value, like say the largest green or the second largest green V star, belongs to this window from A to M times A. So if somebody has given me a M approximation to the value of this, value of the optimal element, I claim that this already implies an order log M approximation for the secretary problem. Okay, so the claim is that, okay, if somebody gives me some poly M range on the benchmark on the largest green or the second largest green, then it already immediately implies a log M approximation. And the idea is very simple. Just do exponential buckets. So define log M levels, like the first level is say from A to 2A, second is 2A to 2 square A, 2 square A to 2 cube A, and so on. So you have these logarithmic number of levels. What my algorithm could always do is just select one of these levels uniformly at random. Okay. So there's at least a 1 over log M chance that you will select a level which contains this, like the largest green element. So once you select that element, and so then I'm guaranteed, like what my algorithm is, I'm going to choose this level. Suppose the level is like say 2 to the I times A to 2 to the I plus 1A, then I'll set a threshold of 2 to the I times A. I'll set the lower bound of this level as the threshold, and I'll select the first element which comes above this. And that gives me a 2 log M approximation, because with 1 over log M probability, I'm guaranteed to select the level which contains this green element. And once I set that as the threshold, I'll select something which has value nearly V star up to a factor of 2. So I basically get a 2 log M approximation. So this is like a very simple idea. Like, so let's make sure this is like everybody's understanding. Or any question there? Like, yeah, it's just a simple argument that if you have M ranges, you can define these exponential buckets. And yeah, one of these buckets contains the element, so you can guess it. So again, like, yeah, the crucial thing here is your claim is on the expected value of your algorithm. I'm not claiming anything that I'm getting this value with high probability or any such thing. So I just want to optimize the expected value of my algorithm. Okay, and right now commenting on the second assumption, like the one where you were assuming maybe something about V star or like the max or the second max green. So one, like what will happen is roughly is that suppose I don't know the estimate of this V star, the largest green or something at t equals 0. But suppose somebody gave me the estimate of this V star by t equals half. I'm still in a good position, because basically I can do this exponential bucketing trick only in the second half of the input. And the largest green is guaranteed to arrive in the second half with like say half a probability. So at least with half a probability, you'll get a 2 log M approximation. So maybe you get like a 4 log M approximation. approximation. Okay, so this idea, that's the kind of the hope that assumption B kind of often reduces to assumption 1, because you can use the initial part of your input to get some rough scale of the benchmark, and then you can repeat the same algorithm. So that's the high level idea, how you go between the assumptions. Okay, so the plan for the algorithm will be as follows, like for the single item problem. So I'll basically partition my entire time horizon into some disjoint intervals, small intervals. And in each interval, I want to kind of get a better and better estimate of the scale of the problem. So at t equals 0, maybe let's work with the assumption 1. So maybe I start off with like an M approximation. Gradually, I want to reduce this scale, like factor M. I want to reduce this M, because if I make this M smaller, I'm always guaranteed a log M approximation. So if M becomes smaller and smaller as a function of N, then I'm already improving. So what we'll do is we'll divide partition into intervals. And the idea of any interval would be the following. Either we'll argue that some simple algorithm inside this interval, so it maybe runs just the Dinkins algorithm, but within this interval, like from this time window, then you can argue that either this algorithm already works well, or if this algorithm performs poorly, then you can get a better estimate on the scale of the problem. So you'll basically refine this estimate or get a better estimate of the scale. And now you might wonder, okay, how do I know whether simple algorithm work or can I get a better estimate? But the good thing is you want to only get expected guarantees. So you can randomly in the end select one of these algorithms. So if any of these algorithms is guaranteed to succeed, then okay, you have a decent chance of selecting one of these algorithms as long as the number of algorithms is not too much. So up to like constant factors and so on, I don't care about it. So yeah, so that's the high level idea. And I'll make it more concrete on the next slide. Good, so let's start off how I can use such an idea to already get a log n approximation for the problem. So under assumption 1, where I'm already given a poly n approximation to opt, I'm already done because this slide already shows that m can be assumed to be n, and so you already have a log n approximation. Now let me show how I can get a log n approximation under assumption 2 as well, whereby my benchmark is the largest green. So it's a simple kind of a case analysis. So case 1 is where you assume that every red element that arrives before t equals half, imagine all of them are smaller than the largest green. Okay, so this is a case where this is a situation where maybe the adversary presents you some of these red elements, but none of them is super large. They're all smaller than the green element. In this case, we already know that Dinkins algorithm will already work. So if I just run the Dinkins algorithm between t equals 0 to half, which basically means I'll set another threshold at t equals a quarter and then select the largest element above that and so on. So that algorithm will already work fine in this special case because all the elements, if I set the threshold to be this red element or the second largest green, either of them will allow me to select the largest green. Okay. A second case is where there exists a super large red element. So imagine there exists a red element which arrives up till t equals half, which has a value which is n times my benchmark. So it's like insanely large. Now the thing is, like if I run a simple algorithm which just selects one of these n elements uniformly at random, one of the entire input, the expected value of this algorithm will again be comparable to the benchmark because with 1 over n probability, you'll get n times v star and then you're done. So the expected value, remember, like, this is where I'm crucially optimizing again, the expected value of my algorithm. Okay, so if I'm either of the case 1 or case 2, I'm already done. Like look at the worst case instance that the adversary presents. If it falls in case 1 or case 2, then I'm already done. Otherwise, in some sense, the adversary has to present me some red element up till t equals half, which belongs to the range v star to n times v star. So this is the third case. So otherwise, in this medium case, there exists a red element which arrives before t equals half with a value between v star and n times v star. And now this is kind of reducing my problem back to assumption 1, because this immediately gives me a factor n approximation to the value of the opt or to the benchmark. So I basically have a factor n approximation, and so I know the scale of the problem up to a factor n. And hence I can again repeat the argument from the last slide and get a log n approximation. So this is basically, yeah. So this is what I'm calling it, kind of like, yeah. So you get, like, I'm refining in the sense, okay, in the beginning, I didn't have any idea on the scale of the problem, but here, like after this interval, after t equals half, I have a factor n approximation. So I've in some sense reduced the scale of the problem from infinite to factor n. And then, okay, you can define these log n levels and again do the same kind of an argument that guess one of these levels, then you'll succeed with probability 1 over log n and select the first element in that level. Okay, so that's the idea.
So a question.
Yeah.
So what does the algorithm do? The algorithm sets the scale using the largest item in t equals to 0 to half in the medium case, I'm thinking.
Yeah, so in the medium case, what the algorithm does is the following. It will look at the largest element that arrives in the first half from t equals half. What's known is that this largest element is like a factor in approximation to the true maximum, to the largest green. So it will basically choose like log m levels, maybe above and below this, choose one of them uniformly at random. And that level, at least with 1 over log m or 1 over 2 log m probability, is guaranteed to contain the largest green. So if that's correct, then you'll set that as the threshold and select the first element in the second half, which belongs to that level. And yeah, so you're guaranteed to succeed. And again, like as I was saying, you might wonder like, okay, how do I know whether I'm in case 1, case 2, or in the third case? But it doesn't matter because I only want an expected guarantee. So I could just run one of these 3 algorithms uniformly at random. And there are only 3 algorithms. So in expectation, like up to a factor of 3 in approximation, I don't care which case I'm in. So that allows me to get a log n approximation. Yeah, so any questions here? Yeah, because it's like a simple idea, and then like to get better like Logstar N and so on, we'll basically apply such an idea recursively. Yeah, again, like the main takeaway I want to say is that okay, if you have a scale of the problem, rough scale of the problem, then you are in a good position because you can define these levels. And how you're going to get the scale of the problem is again using these elements from your input. Either you argue that okay, one of the simple algorithms already works fine, like running the Dinkins algorithm or selecting a uniformly random element. Or you can argue that, okay, this input, you can already use the initial part of the input to get a good estimate of the scale. And in this case, what I'm basically using is the largest element that arrived till t equals half in the medium case to argue that this element is like up to a factor n, the largest green, and hence I can just select it. Good. So I'll maybe quickly go over like how you apply it kind of recursively using 2 checkpoints to get a log n, and then Logstar N. Basically, you do this again multiple times. So what you do for log n is basically rather than dividing the entire time horizon into just 2 intervals, now I divide it into 3 intervals. You again repeat the same kind of an argument in the first interval from time 0 to 1/3. So what will basically like arguing like the same kind of an argument from the last slide will allow you to argue that there exists a red element in this interval which has value between v star and n times v star. Like you have a factor n approximation to the value of opt. Otherwise, you're kind of already done by one of these other simple algorithms. And now once you have this, you can again define like a similar kind of a done or a refined situation. Either you run just the Dinkins algorithm in this interval from 1/3 to 2/3. Like if all the red elements are below v star, then you are done. You like your benchmark because Dinkins algorithm work. Otherwise, if there's like one large element which is super large, then you are done. The main thing that changes is the definition of large. Earlier, I was saying an element is super large if it's n times the benchmark, because with 1 over n probability, you'll get one of them. But now you'll define an element to be large if it's log n times the largest element. Simply because like you already have like a log n approximation. So somehow like if your element is already like log n times b star, you already have like 1 over log n chance of getting it. Hence, already the definition of large is kind of changing. So it's becoming narrower and narrower. So in each interval, you're defined like setting a smaller interval for your benchmark. And otherwise, like if none of these case 1 or case 2 happens, then you can kind of refine. You can argue that by the end of second interval, like basically by time t equals 2, 3 or 2 over 3, you have now, rather than a factor n approximation, you have a log n factor approximation to the value of the benchmark. And hence you get like m becomes log n, so you get like a log n approximation. So again, like a similar kind of an argument. Is okay. Yeah, I'm not sure if I'm going too fast here. Like, so maybe a quick question might help.
So why? So this number of algorithms, will it be θ1 even for Logstar N?
That's a great question. So yeah, so it turns out that's why I'm like what the algorithm I'm presenting you is a Logstar N squared approximation right now. So for multiple checkpoints, because yeah, the number of algorithms becomes, rather than θ1, it becomes Logstar, like order Logstar N. So you get a Logstar N squared approximation using a similar idea what I just presented. to improve it to Logstar N, you have to do a little more work, but I'll not get into it like today. It's like one has to be more careful about how you define these intervals and how you do the calculations. But yeah, so, but that's a very valid question. And as you're asking, like, yeah, so Logstar N, again, you do the same thing. You just divide the algorithm into more like Logstar N interval and argue again that in each interval, either you are in case one, which is the small case, or the large case, or if neither of those simple algorithms work, then you are in the medium case where you can get a better estimate of the scale of the problem and you'll continue refining. And by the end, basically the last interval, you'll already have a very good estimate of the value of opt and you're done. So that's the main. So this was the first part of the first technical result. And again, like the main takeaway I want to give here is more about this idea of learning the scale of the problem. This is an idea which we'll kind of also be using later on for the packing linear programs. So getting here, like, so what we talked about here was this Logstar.
Quick question before you.
Yeah.
So like, can you, so I guess I'm trying to figure out where it, like, at least technically, what is the place where looking at the second largest green element is helping us? So is that easy to, or like relatively easy to see? Like, so instead of competing against the best green you are in this proof sketch, is it like conceptually easy to see why that helps?
Yeah,
like
so basically, like to argue like at many of these locations where that why your secretary algorithm works, you have to use the fact that you have like kind of two green elements.
Okay.
Like, yeah, so, and yeah, I mean, yeah, so this is where you have to be careful. Like often when I'm saying like I'm conditioning, like I have a good estimate of the scale of the problem, the way I usually do it is I basically imagine that maybe say the second largest green arrives in that interval, and that gives me like a good estimate of the scale of the problem. So conditioned on that element arriving, maybe let me not change the slides too much. Yeah, so that's the kind of assumption you have to make. Yeah, basically like you sacrifice one of the elements to get a good estimate of the scale of the problem. And as I'm saying, like, yeah, if you make assumption one that you're already given a Pollyan approximation, then anyways it's not required. But yeah, otherwise you kind of argue this.
So I guess like if you had something stronger, like some small, like let's say, I mean, log n of the top green values are roughly the same. Could you like do
Could you do
like,
it better?
Yeah,
that's a great question.
Well, just to be kind of paying homage to symmetry, like let's say Logstar N of your top green values are exactly equal, in fact.
So
the adversary doesn't even get to pick them, or like pick the value, but they all become equal.
So I guess maybe your question is like, what if I make a slightly stronger assumption? Like maybe some of these larger few values are already, like all of them are comparable. Then can I get a constraint approximation, for instance? Yes. And I think definitely at some number it does work. I forget now what exactly did we know. But an important open question, which is not clear to us already, is actually even under this assumption that just the largest and the second largest are nearly the same, can we get a constant approximation? So that's open. So we can get a Logstar N approximation now. But an interesting open question, which we already don't know, is maybe this assumption already suffices to get a constant approximation. So maybe you don't even need to assume more, like, for instance, like all the Logstar N numbers are the same. But yeah, you have a very valid point. Like, so having a stronger assumption, that definitely helps. I forget exactly what threshold I have to assume.
Okay.
Yeah. But yeah, great point. So a quick question, how much time do I have? I'll accordingly pace up the next section.
About 10 to 12 minutes.
Okay, then I'll go pretty quickly over this packing integer program section. And again, I'll mostly maybe highlight what are the main ideas. Okay. So yeah, so what is this packing integer or packing linear program model? So again, you have this time going from 0 to 1, and these elements arrive one by one. So I've placed them like uniformly, but okay, they arrive like independently. And let's first talk about maybe the fully stochastic model, because the Byzantine model is, as you might naturally extend, like this robust model. So again, these numbers, or like now I'm calling them boxes, they have some values which are going to be revealed to you one by one as an element arrives, but they have a size as well. So earlier, in some sense, the size of each element was just 1, and you had overall capacity of selecting one element. So you could only select one. In this case, I'm thinking of each element has a vector size, like a d-dimensional size. So in some sense, what am I thinking of? Like you're maximizing this LP summation over I v I x subject to ax less than equal to b. So the ith column of this matrix represents the d-dimensional size of the ith element. Okay, and think of every like A is a non-negative matrix, like between 0 and 1. So you need to select a subset of these vectors, a subset of these elements, such that they sum up to at most b in each of the coordinate. So you have a packing constraint on each of the coordinate, and by like slightly rescaling, you can assume that okay, each dimension the budget is exactly b. I mean, yeah, you could slightly relax these assumptions and so on, but the simplest model is this one, that in each coordinate you have an assumption of a limit of b. You want to select a subset of these vectors to maximize your value. So this is in some sense the offline problem. And we'll assume like b is decently large, like polylogarithmic or something. So it's not, so and where each of these elements are bounded in size by 1. So basically like between LP and integer program, it doesn't matter much because you can just do randomized rounding. And because b is like logarithmic, so like simple concentration bounds hold. So that doesn't make much of a difference. So you basically want to solve such a problem. Offline, it's easy, but okay, online, the challenge is you get to see vi, the ith element, as well as the ith column. And you have to immediately decide, are you setting xi to be a 0 or a 1? Like 0 means you're not accepting it, and 1 means you are accepting the column. Okay, so to give you an example, like you start off with a value of 0 and a budget b. And let's say like you have a 3-dimensional problem. So the first element comes, it gives you a value of 25. And it has, like in the first dimension, it's consuming some size, second and third dimension, and you have to decide whether to take it. Maybe I decide to take it. So it consumes my budget and my value is at 25 right now. Then I get to see the second element and maybe I take that as well. My budget increases and so on. And third element and so on. Like maybe this fourth element I wanted to pick, but because if I try to take it, my budget exceeds in the third dimension, so I cannot take it. So that's the problem. So this is the packing integer program or the packing linear program problem. And in the Byzantine model, as you might expect, like what basically is, it's still the same n elements. There are some like green elements, some red elements. The red elements are chosen by an adversary. And the question is, how well can you do as compared to the optimum solution on just the green elements? So yeah, the benchmark here is the optimum solution on the green elements, maybe minus the largest green element, depending on whether you're working under assumption 1 or assumption 2. Okay, so what we are able to show is that you can get a constant approximation under this, as long as your budget is like at least polylogarithmic. And similar results have been previously shown in the fully stochastic model. They're like a long line of work. So in the ITCS paper, we showed such a result for 1 dimension, basically the knapsack version of the problem. But in the SODA paper, we obtained such a result even for the general packing version of the problem. So maybe a quick question or something like about the model.
So then for d equal to 1, already there is constant approximation even in the stochastic model, right?
Yeah, I mean, constant approximations are easy. Exactly. I mean, the knapsack versions, you can get constant approximations. Yeah. So you're saying like are you asking like maybe you don't need to assume this large budget assumption or something? Like, what's the question?
Yeah. So the general case, like the stochastic model, no assumption of large budget, even then you get a constant approximation.
Yeah. So there you can get
6.5 approximation.
Yeah, exactly. But if you want to get so some of these results in the stochastic model, you can actually even improve them down to, like rather than a constant, you can even get a 1 minus epsilon kind of an approximation. To get 1 minus epsilon approximation, you have to make some large budget assumptions as well. So
yes,
even in one dimension.
This Kesselein's papers, I think, deal with this thing, right? Thomas Kesselin? No.
So Thomas has a paper, Anupam has a bunch of papers, like Mark. Like so there are like there's Nikhil Devanu has a bunch of papers. Yeah. So there's like a lot of work on these secretary kind of models in the stochastic world, but in the fully stochastic world. But yeah, we are able to get like similar results this packing. So maybe let me give you just I'll skip those following slides, but let me give you the high level idea of how the algorithms work. Many of these stochastic models. And okay, one of the challenges immediately that comes as soon as you go to higher dimensions is how do I define a threshold? Like, what do I mean by threshold? In the sense that earlier I could say, like, if I want to take an element, maybe whose value is at least $1,000, I'm willing to take it. Now, if you have a high dimensional object, like you need some kind of like value to size ratio you want to bound. So in a one dimensional knapsack, you usually put a threshold of the value to knapsack ratio should be at least something. But in higher dimensional, now the sizes are vectors. So how do I define a threshold? And the idea which goes back to these stochastic works is to use somehow the dual of the problem. So you have this packing LP, you can define the dual of this problem. So the dual is again some vector which is putting some kind of a price on each of the constraints. So a bit more formally, like what many of these algorithms, like both stochastic and now even these robust algorithms, how they work at a high level is you want to estimate the dual for the problem. So the dual can be thought of as some kind of a d-dimensional vector. Basically, each of the d constraints that you have, each of them gets some weight. So this is but the way I want to view this dual is it consists of two things, product of two things. One is a scalar scale, like this is the scale of the problem, times a distribution, a d-dimensional distribution. I mean, sometimes you can define it in together, but like for this robust algorithms, it's important to view both of them separately. But once you know this dual, I mean, it's a separate question how you are going to find this dual, like estimate this dual under your stochastic model. But once you have this dual, then what can be shown is that if you run a very simple greedy algorithm, whereby you select the tth element, as long as this dual price times the size of that vector, as long as this dot product, this scalar, is less than the value, you'll just select it. So basically, if you just make these greedy decisions, that already gets you a good approximation, like a constant approximation to your problem. So the entire challenge becomes, how can I get a good estimate of these duals? Where the dual consists of two portions. One is the scale of the problem, and one is learning this distribution. Okay, so this is in some sense the notion of like the dual that, I mean, the threshold or price or whatever you want to call it. Like this is the main challenge. In the random order model, by random order, I mean the fully stochastic model, what can be shown is you can use the initial samples to already learn this dual. So things are much simpler. You can like maybe use like first small epsilon, a fraction of your input, to already get a good estimate of these duals and then make these greedy decisions. In the Byzantine world, you have to be more careful. First, you have to do like some kind of, what we end up doing is we actually run two online learning algorithms, these multiplicative weights kind of algorithm. One multiplicative weights algorithm is trying to learn the scale of the problem, like this gamma parameter. So this is kind of similar to, like, suppose I give you a poly n approximation to the value of opt. So think of this scale is roughly like of the comparable to the value of opt, but I don't know what the value of opt is. But if somebody gives me a log, like a poly n approximation, then I can again define like some log n levels, and I can use one of that. Those log n levels basically signify log n experts, and I'm trying to do some kind of an online learning on that scale of the problem. And separately, I run another online learning on the distribution. And together, if you combine both these online learning algorithms, that allows you to estimate. So that's the kind of algorithm that we're able to design. And yeah, so I'll maybe quickly go over the next couple of slides. So like some of these ideas have appeared before, like in a paper of Agrawal Devanur, but they have used this idea more in the fully stochastic mode. Whereas in our case, the additional challenge is learning the scale. So in a fully stochastic model, learning this gamma parameter is trivial because you can already use, like you can get an estimate of the opt very easily from the initial part of the input. But in the robust model, that is not a good estimate. So that's like reason we have to kind of combine it with another online learning algorithm. And yeah, there are a few other challenges, but let me, because of lack of time, I'll just skip over it. So sorry for skipping the next 2-3 slides. Yeah. So, but yeah, the main takeaway I want to say is the idea of using online learning algorithm to learn the scale of the problem. So again, you're trying to learn the scale of the problem. In the single item problem, we did this, like either combine it with some simple algorithm and argue that if you randomly choose between the two algorithms, either you'll get a better estimate of the scale or you're already done. In the packing integer programs, we basically use this online learning algorithm, whereby we have a different expert for different scales. And we argue that, yeah, because you have low regret, hence you will be in a good position, low regret with respect to the best scale. So you'll be in a good case. Okay, so to conclude, so there are a bunch of other results also we show in some of these papers, what can you do about single item probability maximization, whereby your goal is not to maximize the expected value of your algorithm, but the probability of getting the largest element or the second largest green element. So there we can get a log n approximation. We have some results of this form. We also have some results like you can improve the constant approximation to even getting like a 1 minus epsilon approximation, but under the further assumption that the corruption is small. Like all the previous results, I did not make any assumption. Like it could be even that 99% of your input is corrupted, like is red, and only 1% of your input is good. But you can get even a 1 minus epsilon approximation if you bound the corruption. additionally to be bounded by epsilon. And we also have some other results under packing problems. So we also have, like in some other works, results on the profit model. So this is another stochastic problem that has been greatly studied, where these elements come from some known distributions. So maybe, and yeah, if you've not heard the problem, it doesn't matter exactly, but like it's a setting which is related to the secretary problem, but now the arrivals are adversarial, but from known distributions. And here again, like lots of results are known, but they are not robust to augmentations. So what do I mean by augmentations? Like if you somehow increase the values of these numbers, you would expect the performance of your algorithm to only improve. That's the kind of robustness model we look at. Like if there's some underlying distribution, if I add positive noise to it, that should only ideally improve the value of your algorithm. But it may not. I mean, many of the existing algorithms are not robust to this. So that's why we had to design newer algorithms, and this work with Nicole and Bo Wagner, and then with Anupam and all. Yeah. So yes, sorry, because I'll be happy to take questions on this offline after the talk. And yeah, so just to summarize, we talked about this Byzantine Secretary model, where we looked at this single item problem, where we get a Logstar N approximation using this refining the scale, and we get a constraint approximation for these packing linear programs or integer programs using online learning of the tools. And there are many, many open questions, primarily, okay, super constant lower bounds, do they exist? What are the tight approximation factors? And also, like, there are many, many other stochastic problems for which we currently only know kind of average case guarantees. But what if there's some outliers or some adversarial arrivals? What's the right notion of robustness one should study? And how do we go about designing such robust algorithms? Okay, thank you. Yeah, happy to take questions.
So I have a question. So the model assumes in the first case, the model assumes that the items values are fixed by the adversary and the order is decided by the distribution. But if the values themselves are distributed and the order is sort of fixed, that probably changes, right?
So that actually becomes very close to this problem I mentioned quickly in the end, the profit inequality problem. Right. So profit inequality problem is precisely the similar regime where the values are drawn from some known distributions, known independent distributions usually, and then, but the arrival sequence is adversarial. And so there is some work on that, but maybe more to be studied, and I'll be happy to maybe tell you more what's known.
So is that at least on the surface, I mean, vastly different from the model which you have presented now? The random
You're
order
saying
model.
Like the challenges between the two models?
Yes.
Like how comparable are they?
Yes.
So
yes.
Some of the techniques we are able to transfer, but I mean, I think the two models are kind of very different, especially to begin with, like what's the right notion of robustness? So in the secretary model, we have this notion of red and green elements. Like red are the good ones and green.
Yeah.
In the other model, like it's difficult to define a red or the green element because usually you assume when the ith element arrives, you know from which distribution it arrives.
Right.
And now, but that will also tell you whether it's a red or a green element because only you have maybe distributions only on the green elements. So that's why like we have to. So that model of robustness doesn't make sense, the red and the green model. What we study in these works are more of this augmentation model where somebody's kind of increasing the values. Then what can we do?
Right.
And so I mean, I'm saying like in some sense, they're still trying to understand the robustness, but in a very different sounding model. And some of the techniques do transfer, but I think that's more of a coincidence rather than like some maybe technical reason.
And I guess the other thing is that the scale is sort of the problem in the current model you presented, whereas in the profit model, it's less of a problem. The scale to which the items values can, I mean, be there, I suppose.
To some extent, it's still an issue. But you may say like, okay, so fair enough. You're saying like maybe the scale of the problem is less of an issue, primarily because you know the distribution, so you know the expected value of operator.
Yes.
I agree with you. So that's why many of the things become much simpler. Like for instance, for the single item problem, for the profit inequality, with robustness, we can show that already one of the existing algorithms immediately works. So you don't even have to make any changes. Okay. So I agree with you. Like many of the challenges become much simpler in this profit model. Yeah.
Any other questions?
I would imagine lower bounds are like challenging here, right? Like it's a complicated.
Exactly. So yeah, yeah, exactly. So even for so I mean, if one has to show a lower bound, I would say it might be easiest to show in the probability maximization view. Like, so where I want to say that you cannot get an element which is the largest green or the second largest green with at least like say a constant probability. How do I argue that this is not possible?
Right.
And that already turned out to be pretty challenging. And yeah, I don't have a good idea. I guess in some sense, I don't even have a good idea on what's the hard family of instances. I guess once one could guess it, then probably proving it is maybe not that difficult or maybe it's more scalable. But yeah, it's not clear how should we define, because there are like many things, many tricks that an algorithm can potentially do. And yeah, it's not clear how to rule that out.
And I guess one can also, like, this is slightly non-technical, but like one can view this assumption, like the scale assumption, as in the framework of this algorithms with advice, or so in some sense that is what is given to you. It's a
Sure. So now you're saying more coming up with good algorithm, then you're saying like giving like somebody giving me the scale of the problem upfront. That first assumption that can be thought of as like some kind of online learning with advice as well.
Right.
Yeah, I mean I agree with you. I totally agree with you. Yeah, I guess maybe somehow like it seems like this is an even simpler assumption, like having some Pollyan approximation to the value of opt. That sounds like, I mean, you don't even need like a fancy machine learning algorithm for that. But I agree with you. Yeah, could be put in that framework.
Got it.
Any other questions?
Okay, I'll stop presenting.
So if there are no other questions, I'll stop the recording and I'll thank the speaker for the nice talk.
Oh, I didn't realize my video was not okay.